Thus far, in our discussion on how atoms interact, we've realized that we can completely gain or lose valence electrons to attach atoms together to form molecules. On the left side of the screen, we have a sodium atom. On the right side, we have a chlorine atom. And sodium can completely lose an electron, donate it to the chlorine to form a sodium ion and a chloride ion. Because these ions have opposite charges, they're attracted to each other, and we formed an ionic bond. Here's another situation where we can form an ionic bond. We still have chlorine on the right, but now I have a hydrogen atom on the left. This hydrogen atom has one proton and thus one electron. One way the hydrogen atom can become happy, have essentially a full valence shell, is, well, to not have any valence shells whatsoever. It can completely lose, it can donate its electron to the chlorine atom. The chlorine becomes a chloride ion, and hydrogen, which is essentially just a proton now, becomes a hydrogen ion, or sometimes referred to as a proton. Because these two ions have opposite charges, they're attracted to each other, and they form an ionic bond, in this case making hydrogen chloride, sometimes referred to as hydrochloric acid. This is an example of a very strong acid, and we bring it up here as an example of an ionic bond because as we continue and discuss the properties of water and later the properties of acid, it's going to become important to realize acids are held together by ionic bonds. Here we have a hydrogen atom again, and instead of forming an ionic bond, we're going to take another hydrogen atom and, well, essentially overlap the valence shells. When we do this, the two hydrogen atoms can essentially share their electrons, and now if I count the electrons in the hydrogen atom on the left, I've got 1, 2, oh, it's got a full valence shell. The hydrogen atom on the right has 1, 2 electrons, it's got a full valence shell, and I've formed a chemical bond called a covalent bond. Ionic bonds are formed by completely gaining or losing electrons, whereas covalent bonds, like we see here, are formed through sharing electrons. Here I have a similar situation, but instead of two hydrogens, I have a hydrogen and a carbon atom. The hydrogen has 1, 2 electrons in its innermost shell, which can only hold 2. It's happy, it has a full valence shell. However, the carbon has 1, 2, 3, 4, 5 electrons in its valence shell. It needs 8 to be full. In this case, we're going to add 3 more hydrogen atoms, and if we count now, we have 1, 2, 3, 4, 5, 6, 7, 8 electrons in the valence shell of carbon. It's full, it's happy, and in the process we've formed 1, 2, 3, 4 covalent bonds. As we continue our discussion on chemistry for biology, we're going to get larger and larger and larger, more complex molecules. And drawing all the protons and neutrons and electrons can become completely overwhelming. So instead of doing that, we're going to replace it with some symbols. In this case, I have C to represent carbon, H to represent the hydrogens, and each blue line that you see represents one covalent bond, or the sharing of one pair of electrons, that is 2 electrons. Here we have an oxygen atom, and we're going to do the same thing with another oxygen atom, share electrons to form bonds. However, in this case, instead of sharing one pair of electrons, we share 2 pairs of electrons. And if I count in either of the valence shells, I've got 1, 2, 3, 4, 5, 6, 7, 8 electrons. The valence shell is full. In this situation, because I share 2 pairs of electrons, I don't have what's referred to as a single bond, but I formed a double bond. And whenever you see 2 lines between molecules, that refers to a double bond or sharing 2 pairs of electrons. We can even, in some situations, share 3 pairs of electrons. That's referred to as a triple bond. Let's go back to an oxygen atom. I've got 1, 2, 3, 4, 5, 6 electrons in the valence shell. I'm going to throw in two hydrogens. By this time, this should make sense that the hydrogens can overlap their valence shells with the oxygen's valence shell. And if I look at the hydrogen, it has 2 electrons in that innermost shell, which can hold 2, which is still the valence shell because it's the outermost shell. And the hydrogens are full. If I look at oxygen, I now have 1, 2, 3, 4, 5, 6, 7, 8 electrons in its valence shell. It's full. And I formed, well, 2 hydrogens, 1 oxygen, H2O, water. Everybody should be familiar with this. You're probably noticing that instead of putting the hydrogens symmetrically around the oxygen, that is maybe in a straight line, I've put both the hydrogens on one side. This is the way we see water in nature. And if you want to understand why we have both hydrogens kind of leaning towards one side of the oxygen, you're going to have to go to a chemistry class for that. But for biology, we need to realize, water has this interesting or unique shape, this arrangement of hydrogens and oxygens. And because we've got this unique shape, we've got these positively charged protons kind of hanging towards or off of one side of the water molecule, and more negatively charged electrons on the other side of the molecule. So when I draw a simple cartoon representation of water, it's got one side that's just a little bit positive and one side that's just a little bit negative. Now this positive charge and negative charge isn't nearly as strong as the positive or negative you get by forming an ion, like a sodium ion, cation, or a chloride ion, an anion, but it is a difference in charge. And because I've got two different charges on opposite sides of water, we refer to it as a polar molecule. Maybe you can think of the polarity of a battery with a positive and negative terminal, or the poles of the Earth, the north and the south, have opposite charges. Water's polar because there are opposite charges on the two sides. And there are some very important properties that water has because it's a polar molecule. If I pour a glass of water, the water molecules in there aren't just willy-nilly distributed, but generally speaking, the positive poles want to interact with the negative poles because they have opposite charges. They are attracted to each other. A little bit later on, we'll talk about the properties that arise of water because of this polarity. But for right now, we need to realize that water is a polar molecule with a slight positive and negative charge. And these opposites attract. When I form a chemical bond, because of these opposite charges, it's referred to as a hydrogen bond. And when I think about hydrogen bonding with respect to the other two kinds of bonds that we've discussed so far, covalent and ionic bonds, hydrogen bonds are much, much weaker. Covalent bonds are the strongest, which makes sense because we're sharing electrons. And when you physically interact, you would expect to be stronger than if you, completely donate or completely accept an electron to form opposite charges to be held together. The charges that hold molecules together in an ionic bond are much more significant than the charges, the little difference in charge on the two sides of a hydrogen molecule. So hydrogen bonds are the weakest. It's also important to realize that covalent and ionic bonds hold atoms together to form molecules. They are the bonds that build molecules. Whereas hydrogen bonds are going to allow molecules to interact with each other, like a couple of water molecules, but hydrogen bonds don't really build molecules in the sense that we're going to talk about.